Let's continue with another example. We again want to find the null space, the column space, and the other two spaces associated with the matrix. So the example that we want to start with is 1, 2, 3, 5, 1, 2, 3, 5, 2, 4, 8, 12, 3, 6, 7, 13, x1, x2, x3, x4, and this is equal to b1, b2, b3. So this is 3 by 4, this is 4 by 1, obviously this is 3 by 1. So b1, b2, b3. Obviously we want to find when does a x will b have a solution, and for what b's does the solution exist. So this is a, this is x, and this is b. So again, if I do reduced row echelon form, so I do minus 2 r1 plus r2, minus 3 r1 plus r3 in any order. Whether I do this one first or this one first doesn't make a difference. So 1, 2, 3, 5. The vertical line represents the equal to sign, b1. Then I have minus 2 plus 2 is 0, minus 4 plus 4 is 0, minus 6 plus 8 is 2, minus 10 plus 12 is 2, and this is b2 minus 2b1. Minus 3 plus 3 is 0, minus 6 plus 6 is 0, minus 9 plus 7 is minus 2, minus 15 plus 13 is minus 15 plus 13 is minus 2 again, and I have b1 minus, sorry, b3 minus 3b1, b3 minus 3b1. Okay, so this is u, and this is, no, this is not u yet. Wait, I'm sorry. This is not u. We want to get rid of this one. So another step, do row 2 plus row 3. If I do that, I have 1, 2, 3, 5, b1, 0, 0, 2, 2, 0, 0, 0, 0. This is b2 minus 2b1, b3 plus b2. So b3 plus b2 minus 5b1. And this is my u. This is my pivot. This is my pivot. So u, and this is c. Pivot here, pivot here. So pivots. So number of pivots is 2. Number of pivots is equal to 2. So this is the rank. So this is the rank of the matrix. So if this is the rank of the matrix, this implies number of free variables. Number of free variables equals n minus r, which is equal to 4 minus 2 equals 2. So there are two free variables, obviously corresponding to this column and corresponding to this column. And let's find those. I can divide by R2 first. So I divide R2 by 2. I divide R2 by 2, and then I will add it to row 1. So 0, 0, 1, 1. This becomes b2 by 2 minus b1. This is 0, 0, 0, 0. This is still b3 plus b2 minus 5b1. And then I do minus 3 row 2 plus r1. So this is 1, this is 2. It doesn't make a difference because these are zeros over here. Again, this is my pivot, this is my pivot. This is going to be r, and this is going to be d. Okay, so minus 3 plus this 3 is 0. Minus 3 plus 5 is 2, and then I have B1, this is minus 3B2. So I have B1 minus 3 by 2 B2 minus 3 by 2 B2 plus 3 B1 plus 3 B1, which is equal to 4 B1 actually. So this is, maybe I just do 4 B1 here and get rid of this one, and I have, this is my vector 4 B1 minus 3 by 2 B2 by 2 B1 and this one. Okay. So for AX equals B to be solvable, this thing should be equal to 0. B3 plus B2 minus 5B1 should be equal to 0. So column space of A contains columns in U that column space of A contains columns, independent columns in U, or maybe columns in A that correspond to pivot columns in U. Pivot columns in U. So the pivot columns in U are the first and the third one. So this implies column space of A contains the first and third column. And what are the first and third columns? So the first and third columns are 1, 2, 3 and 3, 8, 7. 1, 2, 3 and 3, 8, 7. So column space of A contains columns in A that correspond to pivot columns in U. Why? Because these are independent columns. Okay. What about the null space? So null space of A, so we can directly write, so let me write U again here. For null space, instead of going up and down, for null space, we have 1, 2, 0, 2, 1, 2, 0, 2. This thing is not needed, right? And this is 0, 0, 1, 1, 0, 0, 1, 1, and 0, 0, 0, 0. So we have this pivot, and with this one we have x1, x2, x3, x4. This is a pivot column because corresponds to the first one. This is a pivot column because this corresponds to the third one. Equals 0, and this implies null space of A contains, so number of free variables is equal to number of columns minus the rank R, number of columns n minus the rank R, which is equal to 4 minus 2, which equals to 2. And those free variables are this one and this one. So these are the two free variables. And so this contains I'm not going to write x2 or x4 because we already did that last time. So what we are going to do is directly write it. So x2 is 1 here, x2 is 0 here, x4 is 0 here, x4 is 1 here. So alternately these are zeros and ones. This one 2, 0 goes in here. So this is minus 2, this is 0. So this 2 becomes a minus 2. So this is the negative here. 0 doesn't make a difference. This 0 becomes a 0 here. And for this 2 and 1, because these are on the left of this equal to sign, this 2 when comes here becomes a minus 2, it's the negative, and then when this 1 comes here, this becomes a minus 1, again this is negative. So minus 2, 1, 0, 0, minus 2, 0, minus 1, 1. So these are the free variables. So these are the free variables, alternate take on values 1 and 0, free variables. So these are the free variables, and all others are obtained from the matrix R. Okay. What if b equals 0, 6, minus 6? So this is b1, this is b2, this is b3. So for ax equals b to be solvable, so recall, for ax equal to b to be solvable, we want b3 plus b2 minus 5b1 equal to 0. We want b3 plus b2 minus 5b1 equals 0. b3 plus b2 minus 5b1 is equal to 0. So this is equal to minus 6 plus 6 minus 0 equals 0. So this is all right. So b belongs to the column space of A. Okay. Since b belongs to the column space of A, what is C? So C vector was, what did you write C? Or maybe I just write directly D. So D is, I don't want C actually. So D is, so the last one is 0. This is 0. Second is B2 by 2 minus B1. So B1 is already 0, so we don't care. So B2 by 2 is 3. This is equal to B2 by 2 minus B1. B2 by 2 minus, and this 4B1 minus 3B2. 4B1 minus 3B2. 4B1 minus 3B2. 4b1 minus 3 by 2 b2. 4b1 minus 3 by 2 b2. So this becomes, which is 0. 0 minus 3 by 2 minus 18 or minus 6. This becomes minus 6. Is minus 6 or minus 9? This is 4b1 minus 3 by 2 b2. 4b1 minus 3 by 2 b2. I'm sorry. B1 is 0, so this is 0. This is 0. Sorry. This is 0. This is 0. B2 is equal to 6. B2 here is equal to 6. So 6 by 2 is 3. This is 3 into 6, 18. 18 over 2. So this is minus 9. So Rx, so this implies Rx equals D is, Rx equal to D is 1202, 1202, 0011, 0000, minus 930. 1202, 001, 1000, and or what is xp? Xn we have already found. So xp is simply the free variables are 0. So free variables are 0. Free variables are set to 0. Free variables are set to 0, and this minus 9 comes here. So this is minus 9, and this 3, because this is the equal to line. this line, that vertical line represents the equal to symbol. So this is already on the right, and this one is 3 here, minus 9030. So this is the particular solution, and the null space solution we have already found. So this is all we wanted to do about Rx is equal to D and finding the total solution. So your total solution is actually the sum where x is actually xp plus xn, and xn is this one. This is these two. This is actually xn. Okay. So let's move on to the next topic. So the next topic is just summarizes what we have been talking about. It is on linear independence. How do you find that the set of vectors is independent? Linear independence, basis, and the secret word dimension. So what do we understand by dimension? So what do we understand by linear independence, basis, and dimension? So the goal is to define independence, which actually we have already done in an indirect way. In the independence spanning a subspace, and basis for a subspace, and finally dimension of a subspace. Dimension of a subspace. Basis for a subspace means we need to define set of vectors. What do these set of vectors do? These set of vectors span the space. This set of vectors is independent, and how many vectors are there? That is the number of vectors. Number of vectors is actually the dimension. So this is the relation between the basis. So the set of vectors in a basis need to be independent. They should be spanning, and the number of vectors represents the dimension of a subspace. Just to recall, rank of a matrix counts the number of genuinely independent rows or columns in a matrix. Counts the number of genuinely independent rows, columns. That's fine. Okay. And how do we find that the rows or columns are independent? So the check for independence is this one. So check for independence. So the check for independence is you solve this equation. So suppose C1 V1 plus C2 V2 plus CK Vk equals 0 only happens when C1 equals C2 equals Ck equals 0. This is called the trivial solution. So if this is the trivial solution, TRIVIAL. So if this is the trivial solution, then we say this implies V1 vector is independent of V2 vector is independent of Vk vectors. So you need to prove this one If this happens, then you say the set of vectors is independent. Then you say the set of vectors is independent. Also, if one of the vectors is 0, also if any ck is not equal to 0, then obviously then vectors are dependent. Why? Because the kth vector vk can be written as a combination of others. Also, moreover, if one of the vectors is 0, if v1 equals 0, then set is linearly independent. Sorry, set is linearly dependent. Why? Because then c1 is not equal to 0. It is linearly, and equation is still satisfied, linearly dependent for c1 not equal to 0. Thus, a non-trivial solution exists. Okay, good. Let's look at this example. A equals 1, 3, 3, 2. This we have done before actually. 2, 6, minus 9, 5, and minus 1, minus 3, 3, 0. So this and this column, so A2, A1, so A2 is 3 times A1. Since A2 is 3 times A1, columns of this implies columns of A are dependent. Columns of A are dependent because C1 equals minus 3, C2 equals 1, C3 equals 0, and C4 equals 0. Satisfy C1 V1 or C1 A1, maybe I should call C1 A1 plus C2 A2 plus C3 A3 plus C4 A4 equals 0. What about this non-singular square matrix? So A equals 3, 4, 2, 3, 4, 2, 0, 1, 5, 0, 0, 2. So these are pivots already. So it's a full set of pivots. This implies A is non-singular because has a full set of pivots exists. Full sets of pivots exist. This implies A is non-singular or columns are independent because the values on main diagonal are non-zeros. If I want to write this one, I'll write C1 3, 0 plus C2 4, 1, 0 plus C3 2, 5, 2. Even if I make this equal to 0, this equal to 0, and this has to be equal to 0 for this equal to be 0, because these values are non-zeros, right? So A is non-singular, or columns are independent. Full set of pivots exists. These are all the same equation, same statements. They actually tell the same story. If somebody asks you, okay, what is the definition of a non-singular matrix, and you should say a non-singular matrix means that the determinant is 0 if it's a square matrix, a full set of pivots exists, the columns are independent, and since a full set of pivots exists, and or the null space of A contains only the 0 vector. Why? Because since a full set of pivots exists, this is of maximum rank, equals maximum rank. If this is maximum rank, obviously the number of free variables is 0. Contains only 0. Why? Because there are no free variables. Okay. And again, look back to the first example that we did right now, and let me specify what we get from there. 1, 3, 3, 2, 2, 6, 9, 5, minus 1, minus 3, 3, 0. So if I do, if I do minus 2R1 plus R2, and then I do R1 plus R3, I get 1, 3, 3, 2, 0, minus 2 plus 2, 0, minus 6 plus 6, 0, minus 6 plus 9, 3, minus 4 plus 5, 1. This is a pivot. 1 minus 1, 0, 3 minus 3, 0, 0, 0, 3 plus 3, 6, 2 plus 0, 2, and if I do minus 2 row 2 plus row 3, I will get 1, 3, 3, 2, 0, 0, 3, 1, 0, 0, minus 6 plus 6 is 0, minus 2 plus 2 is 0. So I have this pivot here, So 2 pivots, number of pivots equals 2, equals rank, which is minimum of, this is a 3 by 4 matrix, 3, 4. Number of free variables equals n minus, so maybe I say rank, I'll just do rank on this side, equals rank R. So number of free variables is n minus R, so this is m, this is n, this is equal to 4 minus 2 equals 2. So dimension, I have not done dimension, so wait, I don't want to write dimension right now. Okay, so there are the R non-zero rows, so the R, these non-zero rows, the R non-zero rows, the number of pivots is equal to 2, which means the number of independent columns, so maybe I write here, or this one, I say this implies number of independent columns R equals number of independent rows. So the R non-zero rows of U and R, because when we do reduced row echelon form, only this element is going to change and this element is going to change. Everything else is same. So the row is not going to be non-zero, but the row is still going to be non-zero. It's not going to be a zero row. So R independent. So the R non-zero rows of U and R are independent, as are the R columns with pivots. That's why we have written this one is equivalent to this one. Both are the same. Okay. So to check independence, of columns. So this is what you want to do. To check independence of columns, solve Ax equals 0, and if x is equal to 0 is the only solution, then columns of A are independent. Why? Because there are no free variables. Because there are no free variables. So it's only the free variables that gives you infinitely many solutions. If there are no free variables, obviously the only solution is x is equal to 0. This also means so since there are no free variables, this also implies there is no null space. There is no null space except the origin or again implies columns are independent. So there are multiple statements independent. There are multiple statements that actually give you the same conclusion when the columns are independent. I'll write that down at the end of this lecture. If rank R is less than n, this implies there exists. So this is there exists at least one free variable. There is one free variable which can be non-zero, and the columns are dependent. Okay. Also, if A is m by n, this implies n vectors have m components. It's column vector, have m components, and n is greater than m. So if n is greater than m, this means it's a fat matrix, implies a fat matrix, which means it's like this. Implies it's like this. So there are too many columns to be independent. Why? That is there cannot be n pivots. There cannot be n pivots. Implies rank is less than n. And that's what I said, the rank is actually the minimum of m and n. Or this also means, or every system Ax equal to 0 has infinitely many solutions. uh, uh, with x equal to 0, with more unknowns, unknowns than equations, has solution x not equal to 0. And let me give the last example and then move on to the next one. So if a is 1 2 1 1 1 1 2 3 1 2, so if I do minus row 1 plus row 2, so if I do minus row 1 plus row 2, I'll get 1 2 1, minus 1 plus 1 0, minus 2 plus 3 1, minus 1 plus 2 1, and this is a pivot, or if I want to solve further, I get rid of this 2, so I say minus 2 row 2 plus row 1, this gives me 0 1 1, so pivot here, 1 minus 2 plus 2 is 0, minus 2 plus 1 is minus 1, this implies there is, so this is a pivot, this is a pivot, there is only, so this is a 2 by 3 matrix, so m is 2, n is 3, so there is one free variable, there is one free, so if x, this implies x equals x1 x2 x3 equals, so this is x1 x2, so corresponds to x1, corresponds to x2, because x2 is the second one, corresponds here, x1 is the first one, corresponds to the first column, so this is x3 into 1 on the left of the equal to sign, so this will become a plus, this is plus, this will become a minus, so this minus goes here negative, this 1 goes here negative, okay, and this is a free variable, this is a free variable. So columns are, so the third column, this is a dependent column, this is a dependent column, okay. So what do we understand by spanning? What do we understand by spanning? So if a vector space V consists of all linear combinations of this set W1, W2, WL, then this set of vectors spans the space. What does this mean? This implies every vector in V, every vector in the vector space V is some combination of W's. That is V is C1 W1 plus C2 W2 plus CL WL for some CI. Other WKs can also produce same V. This implies C is not unique. Okay. What about the bases? What are bases? And then dimension. So bases, again, to find if B is a combination of columns, we solve AX equals B. To decide if the columns are independent, we solve AX equals 0. So this implies spanning in column space and independence involves null space. So a basis for vector space V is a set of vectors having two properties at once. Having two properties at once. And what are those two properties? A, vectors in the set. So vectors in the are linearly independent. And this simply means there cannot be too many, without losing independence. And B is they span the space. Cannot be means not too few. So this is a maximal independence set. Cannot add vectors and get maximal independent set. And this is the minimum spanning set. We cannot remove vectors and still span the space. Okay, so every vector, so this implies every vector in V is a combination of basis vectors. Why? Because they span the space. Also, this combination is unique. This combination is unique. And where is the proof? So the proof is very simple. Suppose V is equal to some A1 V1 plus A2 V2, or maybe W, I'll say W. Let me write W here. A1 W1 A2 W2 plus AL WL, and then this is also equal to B1 W1 plus B2 W2 plus BL WL. If I subtract the two, so minus, so I have 0 equals A1 minus B1 into W1 plus AL minus BL into WL. But since this set of vectors WK, K is equal to 1 to L is independent, this implies a1 minus b, ai minus bi is equal to 0 for all I, or ai equals bi for all I. So this representation is unique. This representation is unique for the, and probably you're familiar with I, J, K in 3D space. Probably you're familiar with the I hat, J hat, K hat vectors. These are also, they also form a basis dimensional space. So for 3D space, I, J, K form a basis. However, you need to note, however, V has vector space V has infinitely many bases, infinitely many bases. For example, any 3 by 3 non, for any, for example, the columns of, for example, the columns of any non-singular 3 by 3 matrix can be a basis for 3-dimensional space. This non-singular means columns are independent, implies columns are independent. Since these are independent, they can always span the space. So the last one is, how do we define dimension? How do you define dimension? So a space, a vector space has infinitely many bases, however, the number of vectors in the set, or the number of vectors in the bases is this, however the number of vectors in the set called dimension is always the same, is always the same. This is, so dimension, this implies dimension, also known as degrees of freedom. So, or if I have this U, 1, 3, 3, 2, 0, 0, 3, 1, pivot, 0, 0, 0, 0. So this implies two columns are independent. This implies dimension of column space is 2 and is a subspace of, because there are 1, 2, 3, subspace of R3. So just to reiterate, basis is a maximal independent set that is cannot be made larger without losing independence. and basis is also a minimal spanning set, a minimal spanning set that is cannot be made smaller, and still span the space, So now we are in a position to see what are the four fundamental subspaces, and that is what we are going to do in the next lecture. If you have any questions, you can either email me or we can discuss it on our discussions on Mondays and Wednesdays. Thank you very much.